The rice cultivation process. From nursery to harvest. Rice is more than just a crop. It is the backbone of food security for more than half of the world's population. Across Asia, Africa, and parts of Latin America, rice fields shape landscapes, cultures, and livelihoods. From the moment a tiny seed is selected to the day golden grains are harvested. The rice growing process is a careful balance of tradition, science, labor, and nature. This long-form blog explores the complete rice cultivation process in detail, from seed selection and nursery preparation to transplanting, field management, and final harvest. Understanding rice as a crop. Rice is a semi-aquatic cereal crop that thrives in warm, humid climates. Unlike wheat or maize, rice is uniquely adapted to flooded conditions, which help suppress weeds and stabilize temperature around the roots. There are thousands of rice varieties worldwide, commonly grouped into indica rice, long grain, grown mainly in tropical regions, japonica rice, short to medium grain, grown in temperate zones, aromatic rice, such as jasmine and basmati, glutinous rice, high amylopectin content, sticky when cooked. Understanding the biology of rice helps farmers design the right cultivation strategy for their local conditions. Agroclimatic requirements for rice cultivation. Climate. Rice grows best in temperature range 20 to 38 degrees Celsius, annual rainfall 1.000 to 2.000 millimeters, high humidity during vegetative and reproductive stages. Extreme cold, drought, or heat stress during flowering can drastically reduce yield. Soil requirements. Rice can grow in many soil types, but ideal soils include clay or clay loam soils, good water holding capacity, pH range of 5.5 to 7.5. Lowland rice prefers poorly drained soils, while upland rice requires well-drained fields. Land preparation. Building the foundation. Land preparation is one of the most critical stages in rice farming. Proper preparation ensures good seedling establishment, weed control, and efficient water management. Clearing and primary tillage. The process begins with removing crop residues and weeds, plowing the field using tractors, animal power, or hand tools. Primary tillage loosens the soil and incorporates organic matter. Puddling the field. Puddling is a unique operation in lowland rice cultivation. It involves flooding the field with water, repeated plowing or harrowing in wet conditions. Benefits of puddling. Reduces water percolation, controls weeds, creates a soft seedbed for transplanting. Leveling the field. Field leveling ensures uniform water depth, which leads to even crop growth, efficient fertilizer use, reduced water waste. Seed selection and treatment. Choosing quality seeds. High-quality seed is the foundation of a good harvest. Ideal rice seeds should be pure and uniform, high germination rate, above 85%, free from pests and diseases. Farmers may use certified seeds or carefully saved seeds from previous seasons. Seed treatment. Before sowing, seeds are often treated to prevent fungal and bacterial diseases, improve germination. Common practices include soaking seeds in water for 24 hours, followed by incubation for another 24 to 36 hours until sprouting begins. Nursery preparation. Raising healthy seedlings. Rice seedlings are usually raised in a nursery before being transplanted into the main field. Types of rice nurseries. Wet bed nursery, common in irrigated areas. Dry bed nursery, used in rain-fed regions. Mat nursery, used in mechanized transplanting. Preparing the nursery bed. Steps include 1. Selecting fertile land near a water source. 2. Fine tillage and leveling. 3. Applying organic manure or compost. 4. Creating raised beds for good drainage. Sowing the seeds. Pre-germinated seeds are broadcast evenly on the nursery bed and lightly covered with soil or compost. Regular watering is essential. Seedling management. Healthy seedlings require adequate sunlight, proper water management, protection from pests and birds. Seedlings are usually ready for transplanting in 20 to 30 days, depending on the variety. Transplanting, moving seedlings to the field. Transplanting is the process of uprooting seedlings from the nursery and planting them in the main field. Timing of transplanting. Optimal transplanting time ensures strong root establishment, better tillering. Over-aged seedlings can reduce yield. Transplanting methods. Manual transplanting, labor-intensive but precise. Mechanical transplanting, faster and suitable for large farms. Planting density and spacing. Proper spacing, usually 20 × 20 centimeters, allows better sunlight penetration, reduced disease incidence, stronger tiller formation. Water management throughout the growth cycle. Water is a defining factor in rice cultivation. Flooding at early stages. Shallow flooding controls weeds, protects seedlings from temperature stress. Alternate wetting and drying, AWD. Modern rice farming promotes AWD to save water, reduce methane emissions, maintain yield. Drainage before harvest. Draining fields 10 to 15 days before harvest helps improve grain quality, ease harvesting operations. Nutrient management and fertilization. Rice requires balanced nutrition for optimal growth. Essential nutrients: nitrogen, N, vegetative growth; phosphorus, P, root development; potassium, K, grain filling and disease resistance. Organic and inorganic fertilizers. Farmers often combine farmyard manure, compost, chemical fertilizers. Split application of nitrogen improves efficiency and reduces losses. Weed management in rice fields. Weeds compete with rice for nutrients, light, and water. Manual weeding. Traditional hand weeding remains common, especially in small farms. Mechanical weeding. Cono weeders and rotary weeders reduce labor demand. Chemical weed control. Herbicides are used carefully to avoid environmental damage. Pest and disease management. Common rice pests: stem borers, brown planthoppers, rice leaf folders. Major rice diseases: rice blast, bacterial leaf blight, sheath blight. Integrated pest management, IPM, combines cultural, biological, and chemical methods. Growth stages of rice. Rice growth is divided into 1. Germination stage 2, seedling stage 3, tillering stage 4, panicle initiation stage 5, flowering stage 6, grain filling stage 7, maturity stage. Each stage has specific water and nutrient requirements. Harvesting, the final stage. Determining the right harvest time. Rice is ready for harvest when 80 to 85% of grains turn golden yellow. Grain moisture content is around 20 to 25%. Harvesting methods. Manual harvesting using sickles. Mechanical harvesting using combine harvesters. Post-harvest handling. Proper drying and storage are crucial to prevent mold growth, maintain grain quality. Post-harvest processing and storage. After harvesting, rice undergoes threshing, drying, milling, storage in controlled conditions. Good post-harvest practices reduce losses and increase farmer income. Sustainability and the future of rice farming. Modern rice cultivation faces challenges such as climate change, water scarcity, labor shortages. Sustainable practices include climate-resilient varieties, precision farming, reduced chemical use. Conclusion. The journey of rice from seed to harvest is long, complex, and deeply connected to nature. Each stage, from nursery preparation and transplanting to careful water, nutrient, and pest management, plays a vital role in determining yield and quality. By combining traditional knowledge with modern science, farmers can continue to produce rice sustainably and efficiently, ensuring food security for generations to come. Traditional knowledge in rice cultivation. Long before modern agronomy existed, farmers developed sophisticated systems of rice cultivation through observation and experience. Indigenous knowledge includes lunar planting calendars, water sharing customs, seed exchange networks, and natural pest deterrents using herbs and companion plants. These traditions remain highly relevant, especially in smallholder farming systems. In many Asian countries, farmers still observe the timing of monsoons, insect behavior, and soil smell to determine the right moment for sowing or transplanting. Such knowledge, passed down through generations, complements scientific recommendations rather than contradicting them. Mechanization in modern rice farming. Mechanization has transformed rice cultivation, especially in regions facing labor shortages. Machines such as power tillers, mechanical transplanters, and combine harvesters significantly reduce labor requirements and improve efficiency. Mechanical transplanting ensures uniform spacing and depth, leading to more consistent crop stands. Combine harvesters integrate reaping, threshing, and cleaning into a single operation, minimizing post-harvest losses. However, high initial investment costs and maintenance remain barriers for small farmers. Rice cultivation under rain-fed conditions. Not all rice is grown under irrigated conditions. Rain-fed rice farming depends entirely on seasonal rainfall and is more vulnerable to climate variability. Farmers mitigate risks by choosing drought-tolerant varieties, practicing staggered planting, and maintaining field bunds to conserve water. Rain-fed systems often have lower yields but play a crucial role in food security for marginal communities. Upland rice cultivation systems. Upland rice is grown on non-flooded fields, often on slopes or well-drained soils. This system resembles the cultivation of other cereals and relies heavily on rainfall. Weed pressure is higher, and yields are generally lower compared to lowland rice. Despite challenges, upland rice supports livelihoods in mountainous regions where irrigation is not feasible. Organic rice farming. Organic rice farming avoids synthetic fertilizers and pesticides, focusing instead on soil health and ecological balance. Practices include green manuring, compost application, biological pest control, and crop rotation. Although organic yields may be slightly lower, farmers benefit from premium prices and reduced input costs over time. Climate change and rice production. Climate change poses significant threats to rice cultivation through rising temperatures, unpredictable rainfall, floods, and salinity intrusion. Heat stress during flowering can cause spikelet sterility, drastically reducing yield. Adaptation strategies include the development of climate-resilient varieties, improved water management, and diversified farming systems. Rice varietal improvement and breeding. Plant breeding has played a critical role in increasing rice productivity. High-yielding varieties, hybrid rice, and stress-tolerant lines have helped farmers achieve better yields under challenging conditions. Modern breeding techniques incorporate molecular markers and biotechnology to accelerate varietal development while preserving grain quality. Socioeconomic importance of rice farming. Rice farming supports millions of households worldwide. Beyond food production, it provides employment, cultural identity, and economic stability in rural areas. Women play a crucial role in nursery management, transplanting, and post-harvest processing, highlighting the importance of gender-inclusive agricultural policies. Post-harvest losses and their reduction. Post-harvest losses remain a major challenge in rice production, particularly in developing countries. Losses occur during harvesting, drying, storage, and milling. Improved storage facilities, proper drying techniques, and farmer training can significantly reduce these losses. Rice milling and value addition. Milling transforms paddy rice into consumable white or brown rice. Modern mills produce higher recovery rates and better grain quality. Value-added rice products include parboiled rice, rice flour, rice bran oil, and ready-to-cook rice products, increasing market opportunities for farmers. Digital agriculture and smart rice farming. Digital technologies such as remote sensing, mobile advisory services, and precision farming tools are increasingly applied in rice cultivation. Farmers can now monitor crop health, soil moisture, and pest outbreaks in real time. Smart farming improves decision-making, reduces input waste, and enhances sustainability.